So should we begin, Rahul sir?
Yeah, fine.
Okay, thank you,
I'm
sir.
ready.
A very pleasant evening to all distinguished panelists and participants. Bharati Vidyapeeth's Institute of Computer Applications and Management BVI CAM, in association with the Computational Intelligence Society CIS chapter of IEEE Delhi section, Computer Society CS chapter of IEEE Delhi section, Technology and Engineering Management Society TEMS chapter of IEEE Delhi section, System Man and Cybernetics SMC Society chapter of IEEE Delhi section, Communication Society of IEEE Delhi section, Consultants Network Affinity CNA Group of IEEE Delhi section, Life Member Affinity LMA Group of IEEE Delhi section, Inter-Society Relations IRS Standing Committee of IEEE Delhi section, Industry Relation and Special Interest Group on Humanitarian Technology, Site Standing Committees of IEEE Delhi section, Region 10 of IEEE, with the Associations of Computer Society of India, Institute of Information Technology Professionals, ISTE Delhi section, and IETE Delhi Center as technical collaborator welcomes you all today to this IEEE IETE BVI CAM technical lecture series on neuromorphic computing inspired by brain. According to Geoffrey Hinton, all you need is lots and lots of data and lots of information about what the right answer is. And you will be able to train a big neural network to do what you want. Neuromorphic computing is a branch of computing that seeks to replicate the architecture and functioning of the human brain in computational systems. It is inspired by the brain's neural network, aiming to create computers that process information in a way that mimics the brain's efficiency and adaptability. Unlike traditional computing, which relies on binary processing and centralized processing units like the CPU, neuromorphic computing uses hardware designed to simulate the behavior of neurons and synapses. This allows for a more parallel, distributed, and energy efficient way of handling information, much like how the brain operates. In this session, all-round perspective that how neuromorphic computing is different from traditional computing along with its related trends and challenges would be discussed today. I will first take this opportunity to welcome amongst us our distinguished panelists for the day. We are privileged to have amongst us a galaxy of experts. I would now first welcome us amongst us our expert speaker for the day, Mr. Rahul Agarwal, sir, with an e-bouquet. Welcome to the session, sir.
Thank you.
Dear participants, Mr. Rahul Agarwal, sir, is a consultant, head of technology and operations at CSR 3SR Consultancy. His past associations with Altran, Ericsson, Electronics Software, Hughes Software, CDOT, and HCL have given him extensive experience in software product engineering for global clients spread over Finland, Germany, Italy, France, UK, USA, China, South Korea, Vietnam, to name a few countries. He has worked in a number of technology areas like wireless, datacom, telecommunications, cloud, DevOps, etc. His current interest areas also include neuroscience, cybersecurity, and cyber law. He has published articles on a range of topics, including open source intelligence, neuroeducation, artificial emotional intelligence, etc. He is a postgraduate in technology management, BE computer science, and has a diploma in cyber law. Recently, he has also authored a book titled Neuroscience Unveiled, Brain Science for the Future of Intelligence and Technology, which is also available on Amazon. Sir, we are honored to have you amongst us today, and I would now request you to kindly enlighten the House. Over to you, sir.
Thank you, Dr. Ritika. Thanks for inviting me for this session. It's great opportunity to interact with all of you and share my thoughts and views. So today's session, we are going to talk about neuromorphic computing. Uh, I have created a presentation, so I'd like to share that.
Yes.
Is it visible?
Yes, sir. You can put it in slideshow mode.
Okay.
Yes, sir. Absolutely fine.
Okay. So neuromorphic computing, as introduced by Ritika Mano, is inspired by brain. So as part of this session, we will do coverage of two topics, which starts with what is neuromorphic computing, then challenges which are faced in the traditional computing, and we'll also see how brain learns, then what can be done to mimic the brain, and what are the current players in terms of neuromorphic computing, what are the possible key applications with this computing approach, what are the challenges, and finally we'll conclude the session. So let's start with understanding of what is neuroscience. So neuroscience is the scientific study of brain and the nervous system, which controls each and every aspect of our life. Brain is often likened to the computer. So we say that uh, brain is the computer for us. And in terms of brain technologies, uh, we look at enhancing what is possible to explore brain by using computers. So there are different technologies like neuroimaging, which allows you to look at what's happening inside the brain using neuroimaging. Then neurostimulation is a technique which allows you to stimulate certain parts of the brain to treat certain ailments. Then the brain machine interface is a very exciting field where you can tap into what is happening into the brain by putting some chips or some kind of interface, and using that it can allow uh, to understand what instructions brain wants to give to its limbs, and in case a person is not able to activate those his limbs because of paralysis or some other reason, then those can be tapped and you can handle your uh, prosthetic limbs using just by your thoughts. And brain augmentation is another field where you can look at enhancing the capabilities of brain by augmenting it with some additional devices. So this is a very, very exciting field. And even people like Elon Musk are having huge interest in this field. He has even created a startup called Neuralink who are working in this field very aggressively. So this is what uh, computer science is influencing in terms of neuroscience research and development. On the other side, the brain science or the neuroscience is also helping us advance our technologies. So there are various technologies which are influenced by how the brain works, like technology of neuro AI, in which artificial intelligence is improved by understanding how the brain works. Then neuro VR, which is field of virtual reality influenced by how brain works, and the field of neuromorphic computing, where we are looking at how to enhance the computing capabilities by understanding how the brain works. So this is what we are going to talk about in today's session. So let's start with what is neuromorphic computing. So it's development of computational systems that mimic the structure and functions of human brain. It's a brain-inspired technology in which it seeks to replicate the efficiency, adaptability, and learning capabilities of biological neural networks. And the objective is to overcome the limitations of traditional computing and AI. So let's understand what are the challenges of traditional computing. So if you look at the architecture of today's computers, they are based on an architecture called one human architecture, where memory and processing are separated. So the processor accesses the control instructions from the memory by fetching them again and again. And the data is also stored in the memory. And again, processor uh, fetches the data from memory, processes it, and again stores into the memory. And input is taken separately, and the output is again taken out from the processor. So uh, this requires a lot of power because of separation of processing and memory. Because the data has to be constantly moved back and forth between the processor and the memory, which is very energy intensive. It delays any delays in this bus, which is basically between the memory and the processor. Uh, there could be inefficiencies because of the speed of data transfer, and the speed of data transfer limits the overall system performance. And we also facing physical limits in miniaturizing the components. So we are looking at how hardware can be more compact and more transistors can be fitted into the same space. But there's a limit, physical limit, which is being reached now. And now, if we try to put more and more transistors, then the problems like heat generation, power leakage, and signal interference start showing up. So it becomes very, very power consuming and heat generation. Apart from this, the AI or artificial intelligence as we use today is based upon machine learning, which is a software approach that mimics how the brain learns. And it happens through neural networks when they are exposed to examples of what is supposed to be learned. But it may need to see thousands or to millions of examples to achieve the desired results. So for example, telling the difference between a dog and a muffin. So this is a picture, if you can see, uh, there's a dog and there's a species of dog, and then you have a muffin, and uh, probably the AI cannot very easily recognize the difference between these two. There's another example where finding the difference between a dog and a mop is difficult. So what we find is that computers are great at performing precise calculations with huge numbers. But when it comes to learning and abstraction, computers are nowhere close to the brain. As humans, we don't need to see millions of pictures of dogs before we know what a dog is. So there's a fundamental difference between the way our current machine learning works and the way our brain works. Apart from this, there is also a challenge of power consumption. The deep learning algorithms require huge computational resources and consume significant energy during the training and inference. So NLP models like GPT-3 or models for computer vision run on massive clusters of GPUs consuming enormous amounts of power. But if you look at our brain, it uses just about 20 watts of power. And if we look at an estimate, then if we have to create a similar kind of computer which has the same capability like a brain, it will be of the size of a kind of a city sector, and it will require a complete nuclear plant uh, to energize such a computer. So that's a kind of challenge which we have in terms of the current way of computer architecture. So hence an alternate approach is needed to mimic the human brain and its capabilities. So what's the solution? So solution is coming from the nature, or what we call as biomimicry. So we know that nature has perfected different systems through evolution over time. So like if you look at dirt and water repellent paints, which are inspired by lotus leaves, we have a bullet train design, which is mimicking the beak of a kingfisher bird to improve its aerodynamics. We have designed velcros, which are inspired by the tiny hooks of birds. And They are energy efficient buildings which are designed based upon the termite mounds. So there are multiple examples of learning from nature to design and solve the problems of what we have today. So can we take some clue from that, and how how do we achieve brain's efficiency to uh, find out what can be done in terms of our computing resources? So question is how we learn. We follow a approach of neurons. So the human brain has approximately 86 billion neurons, which are the basic cells of nervous system. Learning something leads to formation of neural pathways. So a neural pathway is a series of connected neurons that send information from one part of the brain to another through electrochemical signals. A new neural pathway forms when we encounter a piece of information for the first time. So for example, experiencing the shape, color, smell, taste of a new fruit, say maybe dragon fruit, will create a new neural pathway. So whenever you see something new, you uh, associate it with some specific name given to that. So brain has now attached a meaning to this specific pattern, and there's a new neural pathway created for that. So the more we think about the dragon fruit, the more the pathway is used and the more dominant it becomes. So as we use this neural pathway more and more, we think about dragon fruit, it will become more stronger. But if you don't think about the dragon fruit again, the connections between the neurons will get weakened and the pathway eventually becomes inactive. So this is a concept which is also known as neuroplasticity. So neuroplasticity says that if we what we have learned, if we keep practicing that, it will be strengthened. But if we stop using what we have learned, then it will get erased, because brain has a very sophisticated system of clearing what connections are being established. What's the difference between human learning and machine learning? Human learn Humans learn through experience, association, and trial and error, using cognitive functions such as memory, reasoning, and intuition. And learning involves multiple ways like shape, features, like forelegs. If you're looking at a picture of a dog, so what are its lags, purr, barking, sound. So, and it adapts to apply learning for some uh, other other dogs as well. So, point here is that brain is doing a sensory integration. So it is getting some information to its eyes, maybe sound, which is barking sound, and maybe some other inputs, and it integrates all those inputs and creates an impression of or what it's seen, or what a dog looks like. But when it comes to machine learning, it is data driven, and it involves statistical pattern matching, works by finding patterns in massive databases. So it needs to look at huge number of data sets to understand what a dog would look like. What are the limitations? It causes limitations like it needs huge data sets, lacks perception and reasoning, and struggles with new data. So if there is a new breed of dog picture which it has to look at, probably it will not be able to recognize that. So that's a kind of difference. Now look at how brain-inspired computing can handle these challenges. So neuromorphic computing mimics the structure and functioning of the brain in hardware and software. Uh, it significantly lowers the processing and energy requirements. It's designed to replicate the way biological neurons work. For example, it works in an event-driven manner. So computations are performed only when events occur, which is a mechanism known as spiking neural networks, or SNNs. It mimics neuroplasticity with mechanisms like spike timing dependent plasticity, or STDP, and it also involves something known as in-memory computing. which is integration of memory and processing in hardware. And it is achieved through memristors or other special hardware. So we will talk about these, uh, but let's first understand what are the advantages of using neuromorphic computing. So if we have AI, which is powered by neuromorphic computing, uh, since the power requirement and the processing requirement are drastically reduced, so we don't need to depend on the we don't need to rely on the cloud computing. So currently AI systems require a lot of learning and require say special processing units like GPUs, and it is not possible to have GPUs at all the edges. So generally GPUs are located at the at a cloud location, and you have to access that location uh, in terms of learning and inferring. Then ultra low latency is result of, again, not going uh, there's no need to go to the cloud, so you can take learning and inference locally itself. Then the power requirement becomes very less, and there's better data privacy because there's no data being sent to cloud, or basically it is remaining locally only, and works in the offline mode as well. So these are the kind of advantages which we get if the AI is following neuromorphic computing. There are different use cases which can be there, like autonomous vehicles. They improve on navigational skills, allowing for quicker course correction and collision avoidance. So since this AI would be faster, it can be a better in terms of navigation. Then cybersecurity could also be better by sniffing the cyber attacks or breaches faster. So you can take quick actions to identify any attack and take corrective actions. Then pattern recognition is much faster, uh, and you can identify uh, speech in patterns in the natural language speech and medical images from very fast. Then in terms of robotics, enhancing the real-time learning and decision-making skills helps in better recognition of objects, and it can navigate the factory, integrate factory layouts, and operate faster in an assembly line. Edge AI is another possibility where it doesn't require too much of processing, so it can be used in devices like smartphones and wearables, and its event-driven nature suits well for information processing needs of remote sensors, drones, and other IoT devices. So there are a number of use cases which can benefit by use of neuromorphic computing. So let's understand how it works in terms of. So we talked about three requirements. One was spiking neural networks. So it's a type of artificial neural network that mimics the way real neurons communicate using spikes of electrical activity. So if you look at now a current artificial neural network, it has an input layer and an output layer. So in an input layer, we get an image of maybe a cat, and we have multiple hidden layers between these two input and output layer, and uh, there are different neurons or the nodes in these hidden layers. So each neuron or the node in this receives inputs from all the input, all the nodes of the neuron input layer, and they apply certain weight. So these are the different inputs x1, x2. Similarly, their corresponding weights w1, w2, and they are multiplied, and then it gives an output including some kind of a reverse feedback, and that gives the output for the next layer in this kind of a neural network. So this is how the current artificial neural networks work, which require a lot of computation in terms of multiplication of input value with the weight, and then summation, and then going to the next layer. Now look at how it happens in case of spiking neural network. So in SNNs, neurons communicate using spikes, just like the brain neurons use action potential to fire an activity. So this is how a neuron looks like. It has a main body. This is called soma or nucleus. And then it has multiple hands which help it connecting with the previous neuron in this neural path. And it has a tail kind of structure which goes and which is called axon, and it has at the end it has multiple axon terminals. So this is kind of structure, and this is a there's a number of such neurons which help in creating a neural pathway. Now a neuron only fires when the input exceeds a certain threshold. So it receives input from these different hands, and when the input voltage has increased to certain level, a threshold level, then it emits a energy, and it's basically called an action potential. So that action potential is transported to the next neuron in the neural pathway, and this way the communication keeps on going on. Now it may happen that a neuron uh, is getting input from uh, multiple branches or multiple hands. So so it would look like something like this, that it starts getting input from one, then gets another one, and it gets another one. So the increase in this voltage becomes faster, and it becomes like this, that it is getting input from different neurons, and it is applying certain weightage, and the weightage is actually in terms of the gap between two neurons. So this is small tiny space between two neurons, which is called synapse. So when this dendrite or the axon terminal of the previous neuron is connected, they have such small gap between them, and it is dependent on the how much usage of that particular path is happening. So the weight is basically in terms of how much this particular synapse is getting used. So naturally, it is creating some kind of a resistance, and that resistance is automatically getting applied over here. So instead of numbers, another aspect is that when we talk about traditional computing, there we are passing on numbers and multiplying them. But in case of neuromorphic computing, the numbers are not used. Rather, the coding is done in terms of timing and frequency of the spikes. So which is also known as temporal coding. So if we have, I think, known about Morse coding, so it is something like that. That the information is being passed on in terms of timing of spikes and the frequency of the spike. And for example, SNN in a smart hearing aid only activates when it detects speech, filtering out background noise efficiently. So spike timing dependent plasticity is the second concept which is applied in neuromorphic computing. So in which brain is fed learning rules are used for spiking neural networks. So in a neural pathway, neurons are involved, and here is a example where we have neuron 1 and neuron 2, and there is small tiny gap between the two, which is called synapse. And the strength of the synapse is dependent upon how much this pathway is getting used. So this concept called neurons that fire together wire together. So that means if this neuron 1 fires before neuron 2. So after neuron 1 fires and then the neuron 2 fires, then this particular synapse gets strengthened, which is basically indicating that this path is getting used. But if the reverse happens, that the neuron 2 fires first and then neuron 1 fires, that means this path is not getting used. And in that case, this synapse will get weakened. So this is the concept of your neuroplasticity, which is getting used in terms of STDP. And the third concept which is used is in-memory computing, which is computing approach where data processing happens directly in the memory. So it mimics brain where neurons and synapses, neurons act as compute and the synapses act as memory, which are co-located. So it reduces latency, increases speed, and lowers energy consumption. And it uses specialized hardware like memristors. So what is a memristor? Memristor is a short for memory resistor, which is a resistance of an memristor changes based upon the amount and direction of electrical current that has passed through it. So it's a kind of a resistor whose resistance changes based upon how much current is passing through it. And once the current flow stops, the memristor remembers its last resistance value. So they can switch between different states, uh, high and low, and much faster than the traditional storage techniques like flash memory. This behavior allows memristor to act as a programmable resistor whose state depends on its history of voltage and current. And there are different technologies which are being used to build memristors. So this is the third technology which is used in terms of building neuromorphic computers. If you compare between von Neumann architecture and neuromorphic architecture, so organization in case of von Neumann is CPU and memory separate, but here we have in memory computing, in IO, in case of von Neumann architecture, it is binary input, binary output, and here it is in terms of spikes. Now let's understand what are the key players in terms of neuromorphic computing. So IBM is one of the main players. They started with developing such processors, and True North was the first processor they developed. It was introduced in 2014, and it simulates over 1 million neurons and 256 million synapses. Then they introduced their next processor in 2023, that was North Pole, and it speeds almost 4,000 times faster than the first one. And it can recognize images 22 times faster and with 25 times less energy compared to the current GPU. Intel is another big player. They introduced a processor called Lohi in 2017, and it has 130,000 neurons and 130 million synapses. In 2021, they introduced the next version, that is Lohi 2, which is 10 times faster than the previous one. And it is also accompanied by a software framework called Lava, which allows you to develop applications on this particular processor. Then they introduced a 8-chip Lohi 2 board, which was introduced in 2022. And in 2024, last year, they have introduced a complete system called Hala Point, which is claiming to be having more than 1 billion neurons, integrating more than 1,000 Lohi 2 processors. So it's a kind of a massive computing power which they have introduced. There are other efforts also happening in this field. One is from Heidelberg University. That project is called Brain Scale S. Then we have something being done by University of Manchester, which is called Spinnaker. And there's another one called Fraunhofer Institute of Photonic Microsystems. They have introduced a project called Tempo. So all these three are more of research-based projects. But we also have companies like BrainChip, which have introduced a processor called Akida, and it's a commercial processor designed for low power AI at the edge. So they have introduced with specific use cases in mind. There's another startup called Inatera. They have introduced a spiking neural processor, which is called T1, and they also have a software development kit called Telamo. So these are some of the efforts which are happening in the research field as well as in the commercial offerings. There's another related concept of neuromorphic sensors, which work in an event-driven manner. So it focuses only on changes rather than capturing the complete frame. So for example, we have this image, and if you look at the pixels of this image, and if this image is moving, then only the changes in the picture would be captured and transmitted. Otherwise, in the normal uh, images, the complete grid would be transmitted at a specified frequency. So that's a kind of a big difference. So it's basically event-based sensing, detects only the changes in the scene. It's ultra low power in terms of power consumption, and because of this, it is having very low latency, and there's a high dynamic range, so it can recognize changes right from the low light to the bright sunlight. And it obviously it uses spiking neural networks. So there are various neuromorphic vision systems based upon such sensors which are introduced. So there's a company called Prophecy, which is working along with Sony, and they have introduced products called MetaVision sensor. And there's another company called Innovation, which is introducing dynamic vision sensors, DVS. And these systems allow you to emulate the human eyes efficiency, and their high speed and low power applications in areas like robotics, industrial automation, drones, autonomous vehicles, and AR/VR. Then a company called SynSense, which has two products called SPEC and Xylo chips. So while the earlier two companies were focusing more on the vision systems, SynSense has processors for other senses as well. So these are designed for always-on applications. It's AI-powered face detection and minimal power usage. They have also for hearing, so smart hearing aids, which allow you to noise filter and speech recognition, and they can be used in autonomous drones with real-time object detection for navigation. So these chips are very useful for applications where you have power constraints, and like in case of drones, and where you have again not too much of computing power at your hand. Then Intel and University of Singapore are also collaborating, and they have introduced neuromorphic touch sensors, creating some kind of artificial skin by using the use of Lohi 2 processor. So again, these are various uh, efforts which are happening in this field. This is being used in industry, like Mercedes-Benz is using Akida processor to integrate it into the in-car AI systems for driver monitoring. So while driving, if the driver starts, there's some kind of, he's feeling tired and he's feeling sleepy, then the cameras can detect that, and they can warn. Similarly, there are smart security cameras which are AI powered, and they can provide surveillance much faster. Then Sandia National Laboratories, which is US based uh, atomic surveillance and uh, security labs, they are using Lohi 2 for cybersecurity anomaly detection. So it is being used in cybersecurity as well, and then it is being used for autonomous vehicles vision for faster reaction time. And Sony and Bosch are partnering to develop smart neuromorphic image sensors. Similarly, it is being used in AR/VR eye tracking, and by using such sensors, you can have more accurate gaze tracking and event-based vision. So companies like Meta and Google are looking at their next generation AR/VR headsets by utilizing a neuromorphic vision sensors. So these are some of the key application areas, like in Edge AI, where we can use for smart care, cameras, wearables, medical devices. So there's no cloud reliance in such cases. Then self-driving cars, you can have faster object detection, can have industrial robots, which can adjust its grip 10 times faster than the conventional AI. Then faster processing of brain waves. Our brain, when keeps on emitting different waves, and the the nature of brain waves at a given time indicates what is happening inside the brain. So you can capture the brain waves and infer from them uh, by using these uh, computing devices. You can infer them much faster. Then low power AI for implantable devices. So as we started with that, the brain machine interface would require some kind of device to be implanted in the brain, and such devices would be need to be having working on very low power, and that could be enabled by using neuromorphic devices. They can also help in having smart cochlear implants, which can be used for adaptive hearing aids, and it can help in developing green supercomputers, which could be needing up to 1,000 times lower power consumption for AI research in comparison to the GPUs. So, what are the challenges? So, creating an efficient software that can fully exploit the potential of neuromorphic hardware. So, essentially, neuromorphic computing requires different algorithms and models compared to traditional AI systems. So the current way of algorithms and the way we have current programs, those are not going to work with the neuromorphic hardware. Then the scalability and adoption, that's another challenge in terms of interfacing with a traditional system. So these are some of the key challenges which are coming in the way of faster adoption of neuromorphic systems. What's the future? In terms of future, it's not just a research concept. It's already powering smart cameras, wearables, medical AI, robotics, and self-driving cars. In the next 5 years, we will see wider adoption of AI edge devices and brain-computer interface, and we will see more energy-efficient AI data centers. So to conclude, neuromorphic computing is a rapidly evolving field with great potential, but is still in its early stages. But while there have been significant advancements in neuromorphic hardware and software, widespread, widespread practical application and commercial adoption remains limited. Researchers are actively working to overcome technical challenges and improve the efficiency and scalability of neuromorphic systems. So I would invite all of you to explore the world of neuroscience. Uh, my book on neuroscience, which is Neuroscience Unveiled, is also talking about uh, how brain can influence our daily life, and how the different technologies are getting influenced by neuroscience. So this book is available on Amazon, and you can have a look at that. So that's all what I had planned for this session. So if there are any questions, I can take up them now.
Sure, sir. Thank you so much for the insightful session. I am sure it has enlightened the participants about neuromorphic computing. And yes, there are certain questions from the participants which like to take up with your permission, sir.
Yeah, sure.
So first question we have, current neuromorphic systems are small and limited to the research labs. These systems may struggle to handle tasks on a large scale. How far are we from realizing large scale complex neuromorphic system?
Yeah, so that is right. As I mentioned that the efforts in this direction are already underway. So in terms of hardware, I mentioned that Intel has already introduced a system which is last year. So they have introduced a system which is more than a billion neurons, and it offers a lot of capacity. But the other challenge is in terms of software. So adapting software, creating software, and making it scalable, that remains a major challenge. So that's something which scientists are continuing to work on. That there are a lot of frameworks which are being created to make it work. Uh, so as I highlighted in the last slide, so maybe next 5 years are going to be exciting time in terms of developments in the neuromorphic computing.
Absolutely, sir. So, next question we have, which neuromorphic computing based processing devices would be available for experimentation or let's say simulation?
So currently, uh, the devices which are being offered by IBM and Intel, these are not uh, available commercially. These are being provided only for research purposes and with collaborations. And the different organizations are tying up with them. So as I highlighted, that Intel is collaborating with, say, companies like Prophecy or different universities like Singapore University to do development in this field. But commercially, these are available from companies like Akida, which is offering a system for uh, sensors. So these are not very big systems, but these can be used to develop some kind of uh, neuromorphic sensors. So you can develop some sensors based system using those processors.
Absolutely, sir. So, one more question we have, when these systems will process large amount of data in parallel, obviously they're going to use a lot of hardware. So at that moment, how would they save power and be like sustainable or more reliant?
Uh, see, the key challenge is that the way we are having our computer systems, these are based upon uh, bits and bytes. Like everything is in terms of digits. But in with neuromorphic systems, the concept is and the coding is completely different. It is in terms of spikes, and timing of spikes and the frequencies. So that's one of the big challenges in terms of building up the large systems. So currently they are more being used for sensors based systems, where you have a stream of inputs coming in, and you can utilize these systems to interpret those streams of bits and kind of pixels, and create system based upon that. But yeah, creating a large computing system, that is still uh, requires more effort. That what I would say.
Absolutely, sir. So another question we have is, how far are neuromorphic systems from actually simulating the human brain?
See, simulating the human brain is, I would say, not very near, because there's a lot which is still uh, unknown about brain. So leave aside neuromorphic computing. Even our current knowledge of brain is very, very minuscule in terms of the actual complexity of the brain. So there are a lot of things which are still not known to the scientists even today, how the brain works. So the current level of knowledge is very, very minimal. And in that case, simulating the whole brain is I would say it's really very, very far off.
Absolutely, so very rightly said. And thank you so much for this wonderful presentation today on neuromorphic computing. Your effort and your research in this field is actually remarkable. Thank you so much, sir. Huda sir would have loved to have a meeting with you after a long time today, but sir is busy with another session which is going on in the campus today. So please accept this token of appreciation and e-memento from the side of Bharti Vidyapeeth BVI CAM as an appreciation for this wonderful session today.
Okay.
Uh, I think it is not visible. Just a minute, sir. So please accept this certificate from our side for
Okay.
this
Thank you.
wonderful session today. And we also have a small e-memento. Thank you so much, sir. Thank you once again for this wonderful session today. Thank you so much.
Thank you.
Thank you, Rahul.
Thanks, Ajay.